Good day, everyone, and thank you for joining us. My name is Hardani Camacho, and I will be the moderator for our presentation. I am a member of Fluor's Office of Technology, which focuses on the technical solutions that Fluor provides to our clients. Our engineers, designers, and experts, in other words, our people, are at the core of our success. Today's webinar is titled Post-Combustion Carbon Capture and Facility Integration. Post-combustion carbon capture is a primary pathway to decarbonizing existing industrial assets and a key technology in supporting global carbon emission reduction targets. Subject to the application, post-combustion capture may be the most technically feasible and economical means of reducing the carbon intensity of existing industrial assets. Post-combustion carbon capture presents technical challenges including low CO2 partial pressure, the presence of oxygen and other flue gas contaminants, low flue gas pressures, and site allocation constraints affecting the carbon capture plant layout. The design must also account for the significant heating, cooling, and power utility requirements, all of which directly affect project capital and operating costs. In this presentation, a holistic approach to carbon capture plant assessment and design is presented. Specific focus is placed on the carbon capture process demand on utility system requirements and strategies to optimize facility integration. Andia, over to you.
Thank you, Hardani, and good day, everyone. For our HSE topic, I would like to talk about the dangers of carbon dioxide release and how we can design carbon capture plants more safely by being aware of and addressing the risks and hazards as more plants come online. So what are the dangers of CO2 release? In humans, CO2 is a normal component of blood gases at low concentrations. However, if inhaled at high concentrations, it can be lethal. In addition to the asphyxiation hazard of CO2 caused by displacing oxygen in the air, the inhalation of elevated concentrations of CO2 can increase the acidity of the blood, triggering adverse effects on the respiratory, cardiovascular, and central nervous systems. OSHA has some CO2 exposure limits. There's the PEL, or permissible exposure limit, which is 5,000 ppmv, or 0.5 volume percent after 8 hours, which is the maximum concentration over 8 hours that is safe for humans. Then there's the IDLH, or the immediately dangerous to life and health limit. This is 40,000 ppmv, or 4 volume percent after 30 minutes. It can cause headaches, dizziness, increased blood pressure, and difficulty breathing. And anything greater than 70,000 ppmv, or 7 volume percent, can cause unconsciousness, convulsions, coma, and death. There have been a couple recent CO2 pipeline leaks, and while the CO2 leaks I will soon discuss occurred with pipelines, the risks and hazards are still applicable to high-pressure CO2 design in carbon capture plants. The first one I'll go over was in Satarsha, Mississippi on February 22, 2020, which now is a completed investigation. A 24-inch pipeline ruptured due to girth weld failure. 200 residents were evacuated. Thankfully, there were no fatalities, but 45 people sought medical attention. The pipeline failed on a steep embankment due to heavy rains in the month prior, which caused soil subsidence, creating axial strain on the pipeline that resulted in full-bore ruptured girth weld failure. The U.S. Pipeline and Hazardous Materials Safety Administration investigation reported several contributing factors to the incident, including not addressing the risks of geohazards in plans and procedures, underestimating the potentially affected areas in the dispersion model, and not notifying local responders about a potential failure of the system. The most recent CO2 pipeline leak was near Sulphur, Louisiana on April 3, 2024, which was only a few months ago, and the pipeline is operated by the same company as in the previous incidents. The same 24-inch pipeline ruptured at a CO2 pump station near Sulphur in the southwest of Louisiana, releasing about 107,000 gallons of gas. The pump station and pipeline were not equipped with alarms or other methods of alerting the nearby residents, so officials mostly used social media to alert residents nearby. Officials issued a shelter-in-place advisory, urging everyone within a quarter-mile of the pump station to close doors and windows and turn off air conditioners. The homes in the leak area amounted to 8, 4 of which were luckily unoccupied at the time of the leak. Of the remaining affected homes, there were no serious injuries or illnesses reported. However, it's important to note that had this leak occurred in a more densely populated area, it could have been catastrophic. So what are some CO2 system design best practices? The installation of point CO2 detectors located directly beside potential release locations. These can be installed at compressor buildings, CO2 line pig launchers, and meter skids. The installation of open path CO2 detectors to detect a large CO2 release in the form of a drifting gas plume. These are installed around the perimeter of a plant. And designing CO2 vent piping for cryogenic temperatures associated with depressuring of supercritical CO2. Lastly, we can use crack arresters to minimize the effect of a pipeline rupture. Crack arresters are typically heavier wall pipe placed at a standard distance along a pipeline to stop a running fracture. How can we avoid CO2 dangers? You want to make sure to never enter a workplace that stores or produces carbon dioxide without proper protective equipment, training, or CO2 monitors. If working with compressed CO2, monitor and ventilate with CO2 safety monitors as required by code. Recognize and be aware of areas where CO2 can accumulate indoors. And finally, when in doubt, leave the area immediately and introduce fresh air. Thanks for listening to the HSC topic. I would now like to give the floor to Matthew Gutscher for the main presentation topic.
Thank you, Andia, and hello, everyone. Thank you for joining today's discussion. Today's Innovation Builders webinar is going to discuss some of the key aspects of a post-combustion carbon capture plant design with a focus on the impact of facility integration. The discussion today is going to cover an introduction to post-combustion carbon capture, including a process overview of the plant, technical challenges to implementation, facility integration and introduction to key utilities, a focus on heat integration and heating utility requirements, which will also include a discussion of power, cooling utility requirements, and finally a few closeout remarks. Post-combustion carbon capture is the removal and recovery of carbon dioxide from low-pressure combustion flue gas that would otherwise be vented to the atmosphere. Removal of carbon dioxide from emissions using post-combustion carbon capture is a primary pathway to decarbonizing existing industrial assets, and this is key to meeting near-term emission reductions as part of the larger energy transition effort. Post-combustion carbon capture is not a new technology, and there's a good amount of commercial operating history that can be leveraged. However, projects have had mixed success, especially when implemented on a large scale. Carbon capture projects are significant capital investment and require clear and reliable regulatory frameworks to support evaluation of project economics. Combined with fluctuations in material pricing and forecast project cost escalations have led to many projects being placed on hold or delaying final investment decisions. Considering this, what are the factors that drive the capital intensity, and what are some of the opportunities projects can pursue to improve the overall economics of the project? These are some of the questions that I hope to provide some insight on today. So let's start by identifying some of the technical challenges that need to be addressed in implementing a post-combustion carbon capture solution. First is consideration of the flue gas characteristics. Subject to the flue gas source, the flue gas could contain high concentrations of oxygen and other contaminants, which can cause the amine-based solvent to degrade over time. Without properly addressing these contaminants in the design of the plant, system performance can quickly drop off from the initial plant performance at plant startup and can be difficult to recover from without a complete flush and replacement of the solvent in the system. For the range of industrial applications typically considered as candidates for post-combustion carbon capture, the concentration of carbon dioxide in the flue gas typically ranges from 3 to 20%. Combined with a low flue gas source pressure, the resulting low CO2 partial pressure results in a low driving force available for carbon dioxide recovery. Flue gases are also vented to atmosphere with limited ability to increase the back pressure at the emission source. As a result, the flue gas has a large volumetric flow, affecting the relative size of the flue gas handling equipment. The blower is also required to provide the hydraulic requirement to overcome the flue gas handling system pressure drop. Second is consideration of the facility layout and identifying where the new carbon capture plant will be located. The carbon capture plant requires a relatively large footprint associated with the large flue gas handling equipment and significant utility cooling infrastructure. Generally, the flue gas handling equipment should be located in close proximity to the emission source to minimize the electrical load demand of the flue gas blower and to minimize the flue gas duct routing requirement. The facility will need to consider the availability and proximity to disposal systems or other CO2 end product markets, including associated offtake costs. The carbon capture plant location should also consider the impact of utility integration with the existing facility, new tie-ins or expanded connections with third-party utilities, and the need to provide additional utility generation infrastructure as part of the carbon capture plant scope of facilities. Third is solvent performance. Low CO2 partial pressure drives a requirement for solvent reactivity, but the solvent formulation will also need to address selectivity to ensure the final CO2 product quality requirements are met. Maintaining solvent quality is the key to consistent long-term carbon capture plant performance. Heat-stable salts generated by reactions between the solvent and flue gas contaminants, as well as degradation products from the solvent breakdown, can lead to solvent performance issues, increased corrosion and fouling of the unit, and increased emissions of ammonia and VOCs. The solvent formulation will need to be resilient to degradation in order to maintain this performance. Solvent formulation is one aspect of a solvent degradation mitigation strategy, but the strategy also needs to include measures for protecting the solvent from conditions that increase degradation, as well as measures for managing and removing the accumulation of degradation products. Commercial amine-based technologies are broadly applicable to a range of industrial applications. In connecting with some of the challenges highlighted on the previous slide, they are effective in recovering CO2 from flue gas sources with low concentrations of CO2, including power and cogeneration applications. For flue gas sources with high concentrations of oxygen, a properly designed system can appropriately mitigate reduced system performance associated with the oxidative degradation in an oxygen-rich environment. Similarly, amine-based technology solutions are effective for flue gases high in other contaminants such as particulates or sulfur oxide species when the right pretreatment steps are applied to the flue gas upstream of the CO2 removal step. While the technology is broadly applicable, carbon capture plant design does not lend itself well to a one-design-fits-all solution. Integration strategies applicable to a refinery application in North America will be very different from those applicable to the cement industry in Europe. Some aspects of the presentation today will provide a regional perspective and will not be directly applicable to all facilities in all jurisdictions, but the intent is to highlight the importance of a customized approach to design for each unique application. One other note I want to highlight is that the landscape for carbon reduction solutions is evolving quickly, and I hope to convey that the concepts presented on facility integration in this session can be extended to apply in the evaluation of any post-combustion carbon capture technology. Post-combustion carbon capture plant can be divided into 4 steps. The first step is flue gas cooling and conditioning. Flue gas from the emission source is redirected to the carbon capture plant. The flue gas is first cooled to meet the desired feed temperature of the absorber, which also acts to recover a significant amount of water condensate from the flue gas. The condensed water from the flue gas is relatively clean from most flue gas sources, and the collected water can be recycled and reused in both the carbon capture plant and base facility water systems. A blower is located either upstream or downstream of the flue gas cooling step to overcome the pressure drop of the flue gas handling system. And generally, locating the blower downstream of the cooling equipment is more efficient and cost-effective design. However, there are many factors that can drive relocating the blower upstream of the cooling equipment. Subject to the contaminant levels in the flue gas, additional flue gas pretreatment steps may be required to condition the flue gas to remove associated impurities and protect the solvent from accelerated degradation. The cooled and conditioned flue gas is then routed to the absorber. The second step is CO2 absorption. CO2 is removed from the flue gas in the absorber through contact with the lean solvent. CO2 is chemically absorbed by the solvent, producing a CO2-rich solvent leaving the bottom of the absorber, and a CO2 lean flue gas or vent gas leaving the top of the absorber, which is vented to atmosphere. The chemical absorption of CO2 by the solvent is an exothermic reaction, and additional cooling is required to remove this heat of reaction and minimize excess water losses from the absorber vent. Colder absorber temperature profiles favor thermodynamics and the CO2 loading capacity of the solvent, as well as reduce volumetric flow rates in the absorber, while warmer absorber temperature profiles improve kinetics and the associated rate of CO2 absorption. These competing effects act to counterbalance each other, providing some flexibility in the design to accommodate a range of acceptable cooling temperature profiles while still meeting the overall CO2 recovery requirement. The third step is solvent regeneration. Rich solvent from the absorber is sent to the regenerator, where heat is applied to strip the CO2 from the solvent. The lean solvent leaving the bottom of the regenerator is recycled back to the absorber. The recovered CO2 leaves the top of the regenerator, where it is sent to the CO2 compressor. The temperature required for CO2 stripping from the solvent results in water boiling in the bottom of the regenerator and produces steam. The steam further acts as a stripping agent of the CO2 from the solvent. At the top of the regenerator, the overhead must be cooled to condense and recover the associated steam generated in the system. The fourth and final step is CO2 compression and dehydration to meet final CO2 product specifications. The CO2 compressor is a multi-stage machine that is typically divided into a wet and dry section. The wet section includes intercoolers and interstage separators between compression stages to collect any condensed water. At an intermediate pressure, the CO2 product is sent to the dehydration unit to remove residual water from the CO2 and meet final product specifications. For CO2 products being sent for disposal via sequestration, this water specification is set to avoid hydrate formation in the supercritical CO2 product. The dry CO2 from the dehydration unit is sent to the final stages of compression and cooled to meet product delivery requirements. So here are a couple photos of the post-combustion capture plant at the Northeast Energy Associates facility in Bellingham, Massachusetts that operated between 1991 and 2005. 330 tons per day of CO2 was recovered from a slipstream of stacked flue gas, equivalent to recovery of a 40 megawatt power plant. You can see the flue gas stack in the top right corner of the photo, with the flue gas routed to the direct contact cooling column in the middle of the frame. Of note is that the flue gas handling equipment is located in close proximity to the flue gas stack, minimizing the flue gas duct run to the carbon capture plant. The stripper is located next to the absorber and gives you a good sense of the scale of the flue gas handling equipment relative to the rest of the plant. In this case, the carbon capture plant was 100% air-cooled, and you can see the banks of air coolers lined up behind the rest of the carbon capture equipment. The relative footprint of the air cooler bays to the carbon capture plant is significant based on the large cooling demand of the process. In this example, the recovered CO2 was used for food grade applications, and you can see the liquefaction and storage and truck loading facilities in the background. So for successful implementation of a carbon capture plant, evaluation of system utility requirements and synergies with the existing facility is key. Utility requirements of a carbon capture plant are pretty typical of any industrial facility and can include steam to meet the carbon capture utility heat requirements, electricity to meet the carbon capture plant power requirements, cooling water to meet the cooling utility requirements if cooling water is available, a heating and cooling glycol system subject to the design and requirements of the plant, raw water or treated water makeup to the system, nitrogen for blanketing if it's required by the design, instrument air for process control, and utility air and utility water systems to support plant maintenance activities. Power, steam, and cooling utility requirements are significant and will likely require either expansion of existing utility systems or dedicated new utility infrastructure. The approach to utility design can have a significant impact on carbon capture plant scope of facilities, project capital costs, and plot plan constraints. So focusing in on the key utilities of heating, cooling, and power, the graph on the left shows the relative energy requirements between these utilities. The graph on the right shows the relative fraction of the total plant capital cost. For established commercially available amine-based solvent technologies, process heating associated with the reboiler demand of the regenerator is on the order of magnitude of 2.5 to 3 gigajoules per ton of CO2 recovered and accounts for roughly 10% of the plant capital cost. Process cooling is in the order of magnitude of 5 to 7 gigajoules per ton of CO2 recovered and accounts for roughly 30% of the plant capital cost when considering air cooling as the basis for the utility cooling medium. I'll revisit this shortly, but where makeup water infrastructure can support cooling water system designs, the cost and footprint associated with cooling equipment can be significantly reduced. The relative energy demand for a base design of the power utility is less than 1 gigajoule per ton of CO2 recovered, which can still significantly affect electrical infrastructure integration considerations and power utility requirements. Carbon capture facility power demand is mainly driven by the CO2 product compressor and the upstream flue gas blowers. It's also worth noting that in some jurisdictions, projects are looking to electrify the carbon capture plant design and completely eliminate fuel as the energy source for utility heating demand, again highlighting some of the unique project drivers that affect optimizing facility integration. So when looking at the utility heating and cooling demand of the plant, the first question that often comes up is there any opportunity for additional heat integration to offset heating and cooling utility requirements? Using pinch analysis is an effective means to evaluate and compare alternate heat integration opportunities on a project. A pinch analysis starts with developing composite curves for the carbon capture facility heating and cooling requirements. In the graph presented on this slide, all the hot streams to be cooled are identified by the red curve and include the flue gas, the absorber overhead, the lean solvent from the regenerator overhead, and the CO2 product compression cooling. And all the cold streams to be heated are identified by the blue curve and include the rich solvent to the regenerator and the regeneration reboiler duty. The two curves are plotted on the same graph and shifted on the x-axis until the two curves approach each other. The point where the two curves almost touch is identified as the pinch point. The vertical gap between the two curves at this location is specified by the minimum approach temperature. The theoretical minimum heating and cooling utility duty requirements can then be identified by the inability to overlap the curves on the left and the right-hand side of the graph. This approach provides a metric for evaluating alternative heat integration opportunities and allows the actual utility heating and cooling demands of a given configuration to be compared against the theoretical minimum. Subject to the flue gas source, the heat integration opportunities within the carbon capture plant design are limited based on the low-grade heat available in the carbon capture process and the temperature profile of the available heat sinks. While the cooling duties associated with carbon capture are significant, as depicted in the graph, the operating temperature of the process limit the opportunities for recovering this energy, and most of the heat generated needs to be rejected to atmosphere through the cooling utility. So, as highlighted previously, the utility heating requirement is driven by the heat demand associated with regenerating the solvent. The utility heating requirement is a major driver of the carbon capture plant operating cost, even in jurisdictions with low fuel prices. There is therefore a significant focus and attention to the specific reboiler duty per unit CO2 recovered when benchmarking and comparing alternative technology offerings. The specific reboiler duty is driven by the energy balance of the carbon capture system. Characteristics of the amine solvent formulation, including the heat of solution and the water concentration of the solvent, have a direct effect on the specific reboiler duty. Solvent formulation is complex and needs to balance multiple performance characteristics in addition to thermodynamic considerations. For the current generation of commercial amine solvents, the theoretical minimum specific reboiler duty is generally estimated to be somewhere between 2 and 2.5 gigajoules per ton of CO2 recovered. In addition to solvent formulation, alternate process configuration schemes can have a direct impact on the specific reboiler duty. Examples include the application of a lean vapor compressor or other heat pump application, or the implementation of split flow processes. Technology providers are best positioned to recommend and evaluate alternative process configuration schemes in the context of their specific solvent formulation and consideration of the viability for their process designs. In many cases, there is a knock-on effect to the balance of plant design, which should also be considered. But ultimately, the best solution is the design that provides the overall lowest cost of capture. A typical base design for a carbon capture heating utility is depicted on this schematic. In the absence of surplus steam from the connected facility, new steam generation equipment is required to supply the utility steam to the carbon capture plant, which also increases facility emissions. Unabated, these emissions can significantly reduce the overall facility net carbon reduction. To maintain net carbon reductions, the emissions from the steam product produced are typically directed to the carbon capture plant as depicted in the schematic. This results in a compounding effect on the size of the system as additional emissions results in additional steam demand. A base case utility boiler design will typically converge on a design that is roughly 20% larger to maintain the desired reduction in carbon intensity of the overall facility. The integration of carbon capture plant designs with combined heat and power generation is a synergy that is generally applicable in locations with access to cheap natural gas or a power market that is predominantly fossil fuel based, such as we have here in Alberta. In these instances, either a cogeneration unit or the use of a high pressure steam boiler with turbine power recovery can provide the steam requirements while offsetting the power demand of the carbon capture plant. Examples of this may include industrial facilities looking to maintain an existing power import or export balance with the utility grid. In a base case utility boiler design, the utility boiler design is only sufficient to meet the reboiler steam requirement of the carbon capture plant, and the emissions associated with utility steam production are on the order of 130 to 160 kilograms of CO2 per ton of steam produced and result in the 20% impact on the carbon capture plant capacity highlighted on the previous slide. In this scenario, the full power needs to be supplied by the existing facility or imported from existing power generation capacity, and the impact to the net carbon reduction of the project is subject to the carbon footprint of the utility power supplied. By making steam at a higher intermediate pressure, emissions will increase, but around 80 to 100% of the carbon capture plant power supply can be offset by the associated power generation, which has a very low carbon footprint as these emissions are being captured. The carbon capture plant scope of facilities and project capital cost increases associated with the addition of the steam turbine generator and a larger carbon capture plant due to the slightly higher CO2 emissions per unit steam produced. Integration of cogeneration unit with the addition of a gas turbine power generator with heat recovery steam generation in place of a utility boiler significantly increases the power generation relative to the same steam demand and results in excess power generation beyond the needs of the carbon capture plant. This creates a power export opportunity, which requires additional project drivers beyond just the carbon capture plant to consider implementation. Again, the benefit of the additional power generation comes at the expense of an increase in the carbon capture plant scope of facilities. But in this case, the additional flue gas generated from the carbon capture cogeneration unit significantly impacts the size of the carbon capture plant relative to just the base emissions. So somewhat counter to the integration of a combined heat and power plant is the use of a heat pump applications and use power to offset the fuel demand of the utility heating requirement. One example commonly considered is the evaluation of heat integration with the CO2 compressor. CO2 compressor power consumption is minimized for a design that directionally operates isothermally and at cold temperatures, generally as close to the cooling utility approach temperature as feasible and represented by the blue line in the graph on the screen. This design approach restricts heat integration opportunities as the heat of compression is rejected as low-grade heat, but favors compressor efficiency and minimizes power consumption. For facilities and jurisdictions with relatively cheap and low carbon power but high fuel prices, shifting the compression profile to a higher cooling temperature isotherm can shift the temperature profile of the compressor cooling requirement to a heat grade suitable to offset the reboiler utility steam requirement. So this is the same set of composite heating and cooling curves I presented on the previous slide and is based on operating the CO2 compressor close to the cooling utility isotherm. If the CO2 compressor temperature profile is increased, the cooling composite curve shifts duty into a higher temperature profile. This allows the heating composite curve to be shifted to the left to maintain the same approach temperature at the pinch point and ultimately reduces the minimum heating utility. The reduced heating utility requirement will need to be evaluated against the trade-off in efficiency and increased power consumption of the compressor. Compressor designs can be extremely flexible to integration opportunities, and it's best to engage the compressor vendor early on in project development to discuss integration opportunities. Whether evaluating the application of combined heat and power systems or the use of heat pumps, the economic benefits of the integration opportunity will be subject to the site-specific considerations and should be evaluated on an individual project basis. Transitioning back to the cooling utility, it's obvious from the previous pinch diagram, the low-grade heat rejected from the system is significant. There are 4 locations in the carbon capture plant that drive the utility cooling demand. The first is cooling the flue gas, which also includes the latent heat associated with condensing the water in the flue gas. The second is removing the heat of reaction from the absorber. The third is the condensing requirement of the regenerator overhead. And finally, the fourth is the CO2 compression cooling we just discussed. When comparing utility cooling options, an evaluation of water versus air cooling is often completed, subject to ambient temperature conditions and makeup water availability. Water cooling facilitates colder process temperature profiles compared to air cooling. I've highlighted earlier the trade-off in absorber thermodynamics and kinetics provide some flexibility to maintain high CO2 recovery performance over a range of process cooling temperatures. However, overall performance will be favored by water cooling and the colder process temperatures afforded. Water cooling requires a significant amount of makeup water and will require disposal and/or treatment of the generated blowdown stream, whereas air cooling will have limited to no impact on facility water systems. Existing water infrastructure plays a major role in utility cooling evaluation. Water cooling allows for a compact and flexible plant footprint. Cooling water exchangers can be located in multi-level structures, facilitating modularization and providing constructability advantages. An air cooling design requires a significant air cooler bay count, which must be factored into plant layout considerations. And generally, air-cooled plants are more constrained and require a larger footprint. Water cooling can provide a significant capital cost advantage when compared to air cooling. Improved heat transfer associated with water cooling reduces exchanger surface area and associated material requirements. For cold climate applications, air cooling winterization requirements can further increase cost differential associated with air cooling. Subject to cooling water design considerations, further addressed on the next slide, using water cooling in place of air cooling has the potential to reduce the overall capture plant capital cost by 10 to 20%. Historically in Alberta, new industrial infrastructure projects have placed a high value on raw water resources. These projects have looked to maximize air cooling in place of water cooling systems to minimize additional loads on freshwater resources. However, when evaluating the retrofit of existing facilities, there may be an opportunity to optimize the overall facility water balance and leverage recycled water streams to supplement the utility cooling water system, either as standalone or as part of a hybrid design, to reduce the overall capital cost of the project. Using an open loop or evaporative type cooling water system as an example, heat rejected by the process to the cooling water system is ultimately rejected to atmosphere by evaporation of the cooling water in the open cooling tower. Cold water from the base of the tower is then recirculated to the cooling water supply for distribution. System blowdown is required to prevent the accumulation of any dissolved species in the loop, and makeup water to the system is required to counter the losses from both evaporation and blowdown. Leveraging a few recent project references, for every megawatt of cooling duty, approximately 50 to 60 tons per hour of cooling water circulation was required. Based on the cycles of concentration considered in the design, makeup to the cooling water system was in the order of 3 to 5% of the circulation rate, which is a significant demand for the large cooling duties required by the carbon capture plant. Condensate recovered from the flue gas provides a suitable makeup water source to the cooling water system, but is only sufficient to partially meet the makeup water demand. Projects must consider raw water availability, additional infrastructure to deliver the water to site, and additional water treatment requirements subject to the source of the water quality. Similarly, blowdown rates can also be significant, impacting facility disposal water considerations and associated disposal water infrastructure. These factors can affect both the technical and economic feasibility of an expanded water cooling system. The benefits of water cooling should not be overlooked, but projects are best positioned to start this assessment with an understanding of the water constraints of the facility being evaluated. Often, a hybrid solution consisting of both water cooling and air cooling provides the most feasible option. For regions that are restricted to air-cooled or hybrid designs, one potential opportunity to reduce the significant capital expenditure associated with the air coolers is to evaluate a reduced dry bulb temperature used for air cooling design. This approach effectively reduces the surface area requirement of the air cooler service, reducing bay count and cost, but at the expense of reduced carbon capture performance during high ambient temperatures. Using Alberta again as a regional example, the seasonal ambient temperature fluctuates significantly between summer and winter, and there's a significant reduction in temperature when moving from the 98th percentile dry bulb temperature typically used for design down to the 95th or 90th percentile. This figure represents an example of the impact of reducing the design air temperature on the CO2 recovery rate and allows a cost-benefit analysis to be completed, which can quantify the capital cost savings associated with a lower dry bulb design temperature versus the CO2 penalty of not meeting recovery when ambient temperatures exceed the design temperature. So this brings us to the conclusion of our presentation. In summary, post-combustion carbon capture projects present many unique challenges. A successful project begins with the right approach: emission sources with drivers in place for capture, a well-planned and engineered facility integration strategy with specific consideration of project and regional specific factors, and a coordinated approach to technology evaluation and balance of plant design. I want to thank everyone again for joining the discussion today, and I'll hand it back to Hardani for the Q&A.
Thank you, Matthew. Now we'll take a moment to address the questions that we've received from the audience. Again, please make use of the Q&A tab to ask your questions and address them to all panelists. So Matthew, here is the first question we've received. The absence of strong regulatory frameworks can impact the financial viability of post-combustion carbon capture projects. How can Fluor support clients in moving their projects ahead?
Fluor has been working with many clients to support post-combustion carbon capture project evaluation in the pre-feasibility phase of the project. And so during this project phase, we've been working closely with the client to evaluate design optimizations and synergies that are unique to the specific facility that we're evaluating, leveraging many of the concepts that were included in the presentation today. The goal of the additional upfront study work is to ensure the design configuration is optimized and fixed early on, and this will effectively mitigate design changes later on in the project execution. Fluor has also been working with clients to look at opportunities in early construction planning and modularization, as well as global sourcing of equipment and materials to minimize the overall project costs.
Thank you. Next question is, what are some of the differentiators of Fluor's EFG Plus technology, and how does the performance compare to other commercial amine technologies available on the market?
So Fluor generally delivers engineering, procurement, and construction projects to clients globally, and we have a strong history of acting as the integrator, working with different technology licensors across a range of technology applications. Fleur Technologies is an affiliate of Fleur that offers licensed technologies predominantly in gas processing applications, of which Economy and FG Plus is one of the technologies offered in the post-combustion carbon capture space. EFG Plus is considered competitive carbon capture technology that's actively engaged in the current market. And if there are further follow-up questions on the technology, we can be sure to connect you directly with representatives from the technology team.
Excellent. Thank you, Matthew. Here's another question. Thanks for sending these in. Please keep them coming. How does excess oxygen impact solvent degradation? And a second part to the question is, what are other contaminants that may contribute to solvent degradation?
Oxygen acts directly as to create the oxidative environment that can lead to the breakdown of the amine. So it reacts directly with the solvent, which produces side degradation products which affect the performance of the solvent. So higher oxygen concentration in the flue gas just increases the likelihood of those reactions taking place. So there's a sort of a direct correlation between the oxygen concentration in the flue gas to the degradation of the solvent being contacted with the flue gas. And therefore different measures need to be put in place depending on the degree of oxygen in the flue gas to protect the solvent from that degradation process. In addition to oxygen, other species in the flue gas that can act to either catalyze or react directly with solvents are particulates. So if there are any fines or particulates in the flue gas, sulfur oxide species generally should be removed upstream in the pretreatment step. They cannot react directly with the solvent, as well as NOx. So any sort of oxidative species will react with the solvent.
Thank you. Next question. Is there a facility capacity limit or threshold after which water cooling becomes the economical option?
In general, it's going to come down to jurisdictional considerations. I'm going to speak from a regional perspective again, but there in Canada or Alberta, the cost of water or raw water resources isn't well sort of published. It's got somewhat of a hidden cost, you could call it. And so it's difficult to do an assessment around the economics associated with that. Water will generally provide an economic advantage irrespective of the capacity of the unit, just based on the significant reduction in capital cost associated with the equipment. So those benefits of reduced capex associated with cooling water just sort of expand as the plant gets larger.
Thank you. Next question. What solutions can Fluor provide to ensure the long-term containment of CO2 to prevent leakage back into the atmosphere, which is a concern with carbon capture projects?
The Fluor has somewhat limited direct involvement in the design of sequestration systems. However, we work closely with third parties implementing carbon offtake projects and collaborate on design parameters such as addressing CO2 product quality requirements and levels on contaminants that can be allowed in the CO2 product, as well as system safeguarding measures, of which Andia highlighted in the safety topic, to ensure that there's a consistent approach to design at the interface of the carbon capture plant with the offtake.
One more question. Can you expand on any differences in project considerations associated with CO2 utilization applications?
I think there's two items worth highlighting. CO2 utilization projects have additional processing steps to convert the CO2 into a final product. And this will likely have implications on the quality of the CO2 product produced, or required, I should say, when compared to CO2 being sent for sequestration. as well as the fact that there are downstream processes that should present additional opportunities for facility integration, including heat integration.
Thank you. Next question. Is there any experience, or are you aware of any experience with high temperature flue gas, say around 500 degrees Celsius? And is it possible to use this high temperature to generate low pressure steam and supply heat to the stripper? Is a heat integration question.
I think the closest that application that I've seen projects evaluate would be direct gas turbine applications that have an exhaust that aren't integrated with an existing facility. So most major industrial facilities will have looked at integration opportunities already to recover that energy or that high grade energy from a flue gas at that temperature. But if you have sort of distributed assets like gas turbine drive applications, you could see high temperature exhaust temperatures. And yes, that would be one of the considerations, would be to look at, from a heat integration perspective, how much of that heat can you recover to offset the fuel demand associated with generating the low pressure steam to the regenerator.
Thank you, Matthew. It appears that's all the questions we received from the audience. Thank you very much for those in attendance for your sort of very good questions. And thank you again, Matthew and Andia, for this informative webinar and the time that you've spent not only today, but in preparation as well. Thank you also to our audience for your attendance. It's been a pleasure being your moderator. Please continue to stay informed of these events by visiting the Innovation Builders page on fluor.com or following our social media channels using the hashtag InnovationBuilders. If you'd like us to send you email notifications of future webinars, please email us at innovation.builders@fluor.com with opt-in in the subject line. We appreciate your attention and thank you again for dialing in. We will send out a compiled list of the Q&As shortly, along with the notification that the webinar recording is available for your replay online. If you have any questions or require additional information, please email innovation.builders@fluor.com and someone from our team will get back to you. From all of us on the Innovation Builders team, have a safe day.